Okay, so now that you have had some practice on how to draw some molecules and to figure out what bonds they're made out of, we can now approximate the enthalpy change of a reaction. Now, how are we going to do this? Well, the way to do this is to think about the formula. And the formula is right here. The enthalpy change can be approximated by looking at the bonds that were broken and the bonds that were formed. Now, the bonds that are broken are, of course, the bonds of the reactants, because we know the reactants come together and their bonds have to break and rearrange to form new molecules. So the bonds that are being broken are from the reactants, and the bonds that are being formed, are the ones for the products. Now, when a bond is broken, you need energy to do this. But when a bond is formed, energy is released, and that's why there's a minus sign in the formula. So the formula really tells you that the enthalpy change of a reaction can be approximated by looking at the energy in the bonds of the reactants minus the energy of the bonds in the products. With the example, you'll see that's actually quite simple. So the example we have here is the following. Methane plus 2 oxygen molecules give you carbon dioxide and 2 water molecules. Here are the structures for each of the molecules. We've already done methane together, we did oxygen together, and as a practice example, I gave you carbon dioxide and water. So hopefully you got those, and if not, here they are. Now, all we have to do is analyze what bonds each of the 4 molecules have. So looking at methane, if you look at methane, in the one molecule of methane, there are 4 single carbon-hydrogen bonds. If you look at the oxygen, there is 1 double oxygen-oxygen bond. If you look at the carbon dioxide, there are 2 double carbon-oxygen bonds. And if you look at the water has 2 single oxygen-hydrogen bonds. Now that's per molecule. However, we always have to go back to our equation. Look at the coefficients in front of each of the molecules, the stoichiometric coefficients. They will tell us how many molecules are actually participating in the reaction. So in total, given that our reaction only uses 1 methane, there are a total of 4 single CH bonds. But oxygen, the reaction requires 2 molecules. So since each molecule of oxygen has 1 double oxygen-oxygen bond, in total, there are 2 double oxygen-oxygen bonds. For carbon dioxide, there's only 1 carbon dioxide that's formed in our reaction, so there will be only 2 double carbon-oxygen bonds formed. And finally, water. Originally, per molecule, there are 2 single oxygen-hydrogen bonds, but our reaction shows us that 2 water molecules are made, and therefore there are a total of 4 single oxygen-hydrogen bonds that are formed. Now that we have all the bonds that are present in our reactions, the ones that are broken and the ones that are formed, we can now approximate the enthalpy change. And here's how we do this. Here I've given you a table that shows all the energies associated with the bonds. Now, depending on what table you have, the values may slightly differ because depending on what temperature, what pressure, or whatever conditions the research was done, the values will differ. So this one I just got straight off the internet, very simple table. There is, of course, one in your book on page 419, which you can definitely use as well. So all we have to do now is look at the energy associated with each of the bonds that we need. Well, we start with methane. Methane, we saw that there are carbon-hydrogen bonds. So where are the carbon-hydrogen bonds in the table? If you look right away, top left-hand corner, there it is. 1 carbon-hydrogen bond has an energy of 413 kilojoules. Now, this table doesn't really specify whether the unit is kilojoules or joules or whatever unit it may be, but most tables you'll see the unit is kilojoules. This one doesn't have it, so I apologize for that, but most tables should have units specified somewhere. So in this case, carbon-hydrogen bond is 413 kilojoules. Next, we look for the double oxygen bonds. So the O double bond O. Where is that in the table? In fact, this table doesn't even have an O double bond O, but it's actually there. It's just hidden. It's right down here with the O2. So each O bond, or sorry, O double bond O has 495 kilojoules. Next, we look for the CO bond, which is right down here, which is gives us an energy of 799 kilojoules. And finally, the OH bonds are up here, 463. So now we have the energy associated with each bond. So now all we got to do is find the total energy of the reactants and the total energy of the products in order to approximate our enthalpy change. So let's start with the reactants. We know in the reactants there are 4 single CH bonds and 2 double oxygen bonds. So since each single bond for CH is 413, we have to multiply that by 4, as you can see by the red font in my calculation here. Since there's 4 of them, 4 times 413. And on top of this, another reactant we have is the oxygen, but there were 2 of them. So that's why it's 2 times 495. That gives us a total of 2,642 kilojoules for the energy of the reactants due to their bonds. If now we repeat the same process for the products. So products, we have 2 double CO bonds, so 2 times 799, and 4 single OH bonds, so plus 4 times 463, and that gives us a total of 3,450 kilojoules for the energy of the products, well, their bonds. And finally, we have our formula, which tells us that the enthalpy change can be approximated by the energy of, the bond energy of the reactants minus the bond energy of the products. So we subtract the two values and we get negative 808 kilojoules. So what that implies is that this reaction that we just saw is actually exothermic because the enthalpy change is negative. Now please don't try to memorize this table. No need to. You'll always be given a table. You always have access to one, so don't memorize it. All you need to be able to do is to perform the calculation and, of course, interpret your result. You should now know that based on the fact that it's negative 808 kilojoules, that this reaction releases energy. And that's all there is to it. So hopefully that wasn't too bad, and I will see you in class.